Swayam Prabha. Digital India. Educated India.
So it's an honor, a pleasure to be here. And I would like to start first talking about my university and my department. And of course, I'm very open and interested in collaborations. I work with a lot of people from different countries, and I don't have enough interactions with people from Indian institutions. So I will be welcoming contacts and possibilities for student exchanges. So I come from the University of Padua, which is located close to Venice in the northeastern part of Italy. And what is relevant about the University of Padua is that it was the only university within the entire Venetian Republic, which was very large, very important state in the republic for more than 1,000 years. Ended in 1797 because of Napoleon. And there was only one university in Padua, and that is why they put a lot of effort and money into the university. The university was actually started in 1222, so we are beyond the 803rd academic year. We have an interesting motto for the university, which is in Latin, Univers Universis Patavina Libertas, meaning that the full freedom of the University of Padua is for everybody. And if you're interested in history, I can explain you further. This is related to the fact that the Venetian Republic was not under the Pope, and therefore it had freedom of research and teaching, which other places didn't have in Italy for a long time. Galileo was a professor in Padua for 17 years, and actually Sideros Nuncius, the book that he published describing Jupiter's moons was written in Padua based on the observation that he had in Padua. If you come and visit the university, we still have the chair that was built for him by his students, and so built for him by his students so that they could see him because he wasn't a very tall guy. So the University of Padua is famous for the medical school because the anatomy field started in Padua, actually by a guy from Belgium called Vesalius, and he was the founder of pathological anatomy. So they started dissecting bodies in Padua, formally being able to teach students from bodies, not just from theory. We have a long list of important alumni. If you're a mechanical engineer, you certainly are familiar with cardanic joints. And Cardanus was a professor of mathematics at the University of Padua, but you can see there just a list of them, including Giacomo Casanova, who was graduated in law from the University of Padua. We also have the world first botanical garden that was created to teach medicine, or actually medicinal plants, to students, and it is still in the original place. And a lot of plants from the New World were introduced into the Western world through the botanical garden in Padua. We also have the first female laureate in the world. She was a Venetian noble. She graduated at the end of the 17th century. And after graduation, she was sent to a convent for the rest of her life, but at least she was a doctor. And she kept studying and working. The university is pretty large. We have about 75,000 students, of which about 13,000 students are engineering students. These are, and the data are a little bit old, but we don't have a bad ranking in the different listings. My department deals with the fields of aerospace engineering, chemical, electric, energy, mechanical, and materials engineering. We have, of course, courses at the bachelor, master's, and PhD level. Currently, we're about 150 faculty. We have more than 200 PhD students, more than 200 postdocs. So we are very interested in, as I mentioned, student exchange and collaboration between different institutions. And personally, I work mainly on additive manufacturing of ceramics, especially from precursors. I have been working for a long time on polymer-derived ceramics. I'm working also on geopolymers now. A colleague of mine is working on biomaterials, and we are also interested in materials for the environment. And this is my group with a couple of colleagues, and some funding agencies from institutions and companies. So I think I can move to the lecture. So in this cycle of classes, I will be discussing additive manufacturing of ceramics. I don't know what kind of background you have in additive manufacturing. The first lecture has the aim of telling you why and when it would make sense, in my opinion, to use additive manufacturing. And the main message there is that you do not necessarily need to use additive manufacturing if that's not favorable in terms of cost or in terms of speed of process or in terms of geometry of the component. So I don't want to put you off the topic, but I'm simply trying to encourage people to use additive manufacturing where it could have the most impact. So this first talk is quite general. So I will be talking about, as I said, why it would make sense and when it makes sense to use additive manufacturing, specifically for ceramics. So you're certainly familiar with the fact that you have three basic principles for the shaping of materials. You have formative shaping. I don't need to read all the list there, but you're familiar with formative shaping, which is applied a lot to metals and polymers, but can be applied also to ceramics. Subtractive shaping is also a very good way of transforming a part into a component with specific shapes. And then since maybe 30 years, additive manufacturing has started. And you can see here a list of the different technologies that can be used. And people say, and I think they're correct, that additive manufacturing is the technology that has potential not only to change the way of conventional industrial manufacturing processes, adding materials instead of subtracting, but it also has potential to create entirely a new production and business strategy. And just for your information, currently it is possible to generate ceramic parts with a wide range of compositions, starting with sizes starting from a few hundreds of nanometers to the meter and beyond. Of course, there are still a lot of limitations in terms of compositions, precision, and all these things that are related to the specific technologies that people are using. One point that I would like to make is that at the beginning, people were referring to additive manufacturing, calling it rapid prototyping. And this shows that the idea behind it was not that of producing components for use or testing, but it was rather simply a rapid way of shaping specific parts and to show the potential that they would have starting from the shape. These days, there's been the transition towards going from rapid prototyping to actual additive manufacturing, where you use this type of technology for making parts that you can use. You're certainly familiar, if you work in the field, with the ISO ASTM standard. I think this is the last one from 2021. Maybe there is a new one in 2025, but things are basically the same. And there are 7 different categories. You can see here 8, but in the standard there are only 7. And they are called binder jetting, material extrusion, directed energy deposition, material jetting, powder bed fusion, sheet lamination, and vat photopolymerization. And they each use different approaches. They have limitations and characteristics, and I will try to discuss some of them specifically with relation to ceramic materials. And let me just mention the fact that these technologies are not enough. People are still trying to develop new approaches. And one of the possibilities is to use what is called hybrid additive manufacturing. So you combine different technologies because, as I will mention, I will hope to demonstrate, each technology has strengths but also drawbacks. So by combining different technologies, people hope to overcome some of the limitations that come with each specific technology. And before continuing, let me just mention one important fact. You're certainly familiar with additive manufacturing carried out using polymers, and you know that you can use a wide range of technologies. You make a part, and the part is final for the most part. You don't need to do any post-processing. The part is already fully consolidated and has the properties that are suitable for certain applications. We can discuss if the properties are the same as the properties that the bulk material would have, but that's a different topic. But the material is finished after printing. For metals, typically you consolidate powders using different technologies, and after consolidation, you have a solid part, and you do not need to do anything else. I mean, you can do post-thermal processing to fine-tune the microstructure. You can do some surface finishing and so forth, but the part is a consolidated metal. With ceramics, all the technologies, apart from directed energy deposition and laser approaches, you're forming parts that need to be further processed thermally. So you have a component that is typically based on ceramic powders and the binder, sacrificial binder, polymeric binder in most cases, and you need to transform that assembly of powders into a consolidated ceramic body. And you do that by thermal processing with a lot of issues, as we will see. So that's one specific characteristic of additive manufacturing with ceramics that is certainly a drawback with respect to other technologies. We will see that using SLA or SLS with ceramic powders is not that convenient, as well as directed energy deposition. There are some people working on this technology because those two technologies would enable you to not just shape the material, but consolidate by sintering in situ the powders. So that would be the holy grail, if you can do that, the holy grail for ceramic additive manufacturing. But those technologies have a lot of problems, and the parts that you can generate do not possess yet the properties that are required for application. So people use mainly technologies where you shape the component and then you need to transform it into a bulk, into a consolidated sintered ceramic part. So this is a little bit trivial because you're certainly familiar with the fact that additive manufacturing is basically creating objects layer by layer, and what you need to do is to inscribe the layer using different approaches and consolidate the material specifically in a where you want in space on your XY plane. And this leads to some surface features that, certain surface features that can be detrimental or not detrimental depending on the application. For ceramics, I remind you that surface flaws are a killer for the mechanical properties. So ideally for ceramic manufacturing, you would like to have a smooth surface, but there are applications, for instance, catalyst support or areas where you want to increase the geometric surface area of your part, where having surface features might be useful. Certainly, the surface features, the stair-stepping effect, are related to the size of the layer that you're using for generating your part. So you can see here a part, this is a polymeric part, but there's just an example. If you use a 125 micron layer, you can certainly see the steps quite clearly. So one strategy will be to reduce the size of the layer, the thickness of the layer. If you do that, you get a much smoother surface, but you increase significantly the time for fabrication, which is not really what you want to do. Let me just mention that what is true for this type of additive manufacturing is actually not true for a new type of additive manufacturing, specifically for volumetric additive manufacturing called volumetric additive manufacturing. VAM, volumetric additive manufacturing, builds a part within the volume of a liquid, and therefore the part is not built using a layer-by-layer strategy. And this leads, for instance, to smooth surfaces, which is quite nice to have. So there are certainly quite a list of advantages for additive manufacturing technologies. You can see them there. You don't need tools and molds, and they are expensive, especially for ceramics, because they are hard materials. You have a fast time from design to product. For small series production, they're cost efficient. Certainly, you can make a wide range of highly customized products. And we shouldn't forget that with additive manufacturing, you can obtain geometries that not only would be difficult and expensive to generate using conventional manufacturing, but you can generate components that you would not be able to manufacture using traditional approaches. Also, another significant advantage is that the cost per part is not influenced so much by the complexity of the geometry. And that's certainly not a strong advantage with respect to traditional technologies. And you can see other advantages there. So these are classical images that you can find, there is a reference there, that shows that for traditional manufacturing, you typically have a decrease of cost with increasing per part, with increasing the number of parts that you're manufacturing. This is related to the fact that tooling is expensive. And it means that while for additive manufacturing, you do not have this economy of scale, you do not have this effect. And this makes the possibility of generating a limited number of parts, but highly bespoke, highly architected for specific applications or customers. This makes the strength, shows the strength of additive manufacturing, because you can get basically the possibility of having individualization for free. Another another chart that people show is that the cost per part with traditional manufacturing increased rather steeply with increasing the customization, the complexity of the part, the number of variations that you need to have in your part. While with additive manufacturing, printing a simple part or simple design or a more complex design part is not an issue. So again, above a certain threshold, you can see that additive manufacturing really provides a strong advantage, because basically you obtain complexity for free. Another point that I would like to make is that if you look at the cost per part with respect to the distance from the manufacturing to the place where the part is used, with traditional manufacturing, you have an increase of cost with the distance because of shipping, of course. But with additive manufacturing, you could certainly have a way of distributing the designs to different localized factories. And in this way, you can have advantages in terms of additive manufacturing being more economical when you have to send parts far away from your single factory, specialized factory. I will not talk a lot about applications of additively manufactured ceramics. I will be talking more about shaping, about fabrication rather than applications. But I just want to give you a couple of examples here that show that the advantages of additive manufacturing. So this is a catalyst carrier that was designed by Fraunhofer KTS in Germany in collaboration with the company Litus, which is an additive manufacturing provider of printers in Austria. And you can see that by computation and now with artificial intelligence, you can actually drive the design of the part towards using the architecture of the part as a way of controlling the properties and optimizing the properties of the component. Here in this heat exchanger, there is a completely new design with respect to traditional catalyst carriers with an improved efficiency because you have in situ turbulent flow and you have shorter reaction way and therefore faster reaction time and higher conversion. You can see another example where they show that the cost of complexity when you're using additive manufacturing is no longer a design barrier. So you can see going from a traditional component to a more optimized component where you have less material, you have better mechanical properties, and the part is more lightweight. So there is a tremendous effort going on in the field of additive manufacturing for topological optimization, so computational modeling and optimization of shapes for specific applications. Other application examples, for instance, you can see here zirconia antennas for nanosatellites. This is a very complex high precision component and is also rather large, almost 40 centimeters in size. The bottom one is a gas distribution ring, and these have been manufactured by the company 3D Ceram using stereolithography. So I'd certainly an advocate for additive manufacturing, in particular for ceramics, but we need to be aware of that there are also disadvantages because, you know, as a student, you tend to follow trends because they're exciting, they are novel, and you want to make an impact. But at the same time, you need to be aware that not everything is paved in gold. And the disadvantages for additive manufacturing technologies are that, for instance, printers are expensive. Of course, you can have cheap printers, but then you get cheap part or cheap looking and behaving parts. From the industrial point of view, rather than research point of view, the technology does not provide an easy mean for scalable production because there are limitations to the technology. If you want to make a lot of parts, you need to use a lot of printers. Okay, you cannot simply increase the size of the vat, for instance. So you need to operate in series. And there are also certain limitations in terms of the size of the parts that you can make using additive manufacturing. The production rate per machine is limited by a range of factors, and also the type of material itself poses some issues in terms of what you can do using a specific technology. Certainly, the cost per part is still high. Traditional finishing is still required for many parts. I'm talking in general for additive manufacturing, but specifically for ceramics. And you have precision issues. Maybe it's not listed here, but one of the problems with additive manufacturing is quality control, because often the defects are inside the part. So you do not see them until you use the part and you have issues. So people have to come up, I mean, you can use tomography, of course, but that's quite intensive in terms of cost, expertise, and it's not a really fast technology, so you cannot do inline monitoring easily using this approach. So people are still struggling from the industrial point of view to find a compromise between print quality and characterization and assessment of the properties of the material. Often the properties of the component after being additively manufactured are worse of the same material being shaped in a different traditional way, because, for instance, of the stepping effect, or because of the specific type of defects that additive manufacturing can generate. Often you have anisotropic properties in your part. You can take that into account in your design of the part, but that's certainly an additional challenge. In terms of materials, quite a wide range has been validated. And then here we can discuss, if you are an industrialist, you would like to buy a bottle of material and use that. In that case, the choices are rather limited. If you are a researcher, then of course you can develop your own feedstocks, but companies typically would like to rely on people to provide feedstocks for them. One problem is that there is a lack of talent for additive manufacturing. So people in industry need to hire new people with specific expertise. And additive manufacturing is not taught a lot at universities yet. Certainly it is from the computational point of view, but from the manufacturing point of view, it's less so. I already mentioned that you have 7 different categories for additive manufacturing, and the people working in additive manufacturing in general, they would call direct additive manufacturing a technology that gives you not just a shape, but gives you a material that is ready to use, already consolidated. And they would call indirect additive manufacturing all the technologies that require further thermal processing to obtain your final part. So from that point of view, almost all technologies used for additive manufacturing of ceramics are indirect additive manufacturing technologies. But we can use the same terminology with a different meaning applied specifically to additive manufacturing of ceramics. We can say that direct additive manufacturing is an approach where you deposit the material only in the position that gives you the desired shape for the final object. And these include these technologies: direct inwriting, inkjet printing, or fused deposition modeling. While indirect additive manufacturing is an approach where you deposit a layer or your material, you inscribe a shape of that layer using different approaches, and then you remove the excess powder. And this means, for instance, that you cannot make an enclosed space, enclosed cell, because you would not be able to extract the unbound powder from that area. And these technologies include binder jetting, selective laser sintering, stereolithography, DLP, and laminated object manufacturing. So I'm not going into the details for each technology because there are certainly books available and a lot of sources for you. But I would just want to quickly present the different technologies and highlight some of their working principles and issues that you might have with specifically with ceramic material when using these for ceramic materials. So VAT photopolymerization technologies here, I'm not listing all of them, but you have SLA, which is let's say the original one. You use a laser to consolidate your material layer by layer, and the laser typically comes from the top, and you generate the part, and then you lower the part, the liquid fills the space that you've left, and you inscribe your layer again, and so forth. And another approach is to do the same. So you're basically cross-linking layer by layer using a photopolymer your part, and you lift or lower your body by the thickness that you want for generating the layer. And then you irradiate using a different approach that is based on mirrors and a different source for the light. And the difference between these two technologies is related on the speed, the size of the vat that you can use, and for instance, SLA can be typically larger than DLP vats. But the main difference is the surface quality. DLP generates quite strong stepping effects. So you can certainly see the different layer, the difference between each layer. And if you're using ceramic slurries, then you typically have issues in terms of the distribution of the powders within each layer because of settling issues. So you have typically weak interfaces that you need to consider. These technologies are, of course, used for, they were developed for polymers. They are used also for metals, not DLP, because you need to have something that is transparent to the radiation. So metals will not be suitable for that, because the radiation typically is around 405 nanometers. So it's a high energy, but still at the range of the visible, and the metals, of course, absorb. For DLP, you can have so-called bottom-up or top-down geometries, meaning that you can have the light source from the bottom, or you can have the light source from the top. There are advantages and disadvantages of each approach in terms of the quality of the parts that you can obtain. Note that for the bottom-up approach, there is the clip technology, which has been developed for polymers that allows you to have a continuous printing and fast printing. So for polymers, this works quite well. The issues that you have, and first, let me mention that in order to use these technologies for ceramics, and I'm talking about conventional ceramics, not precursor-based ceramics, you need to have photocurable monomers or oligomers inside your feedstock. You need to have a photoinitiator. You need to have a photoabsorber that allows you to control the penetration depth of the light, and therefore the quality of the part, or certain features inside the part. You might add a diluent if you need other additives, but you certainly need to have ceramic powders. And if you have ceramic powders, what happens is that you increase dramatically the viscosity of the slurry. And this means that if you go back here, you know that every time you shift the layer, you shift the part the gap needs to be filled by your feedstock. And if the feedstock does not flow because it contains a lot of particles, then you have issues in terms of the homogeneity of the layer that next layer that you're generating. So, of course, what you could do is to reduce the number of ceramic particles that you are using for your feedstock. But this means that in the end, your part will have a lot of polymeric binder that needs to be decomposed. And this leads to a lot of issues in terms of gas release, cracking, and also shrinkage, because the less solid ceramic particles you have in your system, the higher the shrinkage of the part, with issues in terms of shape stability, and also it's an issue of cost. So you need to have people use highly loaded suspensions, meaning more than 40 volumetric percent. In terms of weight percent, you can go up to 80 weight percent ceramic particle loading into your feedstock. And you need to have, when you have such highly non-flowable slurries, what you need to do is to have specific printers that spread the layer using a mechanical blade, like a doctor's blade. So in this way, this is the best approach for generating continuous, homogeneous, flat layer of new feedstock that needs then to be photocross-linked. But such machines are quite expensive unless you buy them from China, where the cost is lower. But still, we just bought one. It's about 40,000 euros. But the commercial ones are 350,000 to 400,000 euros. In any case, independently on how much powder you have and what kind of technology you're using for shaping your powder, in the end you have a green part. You have your shaped body, looks nice, has the strength that you need for further handling, but the further handling requires first debinding, the burnout of the polymeric part, and then sintering. And if you're familiar with conventional ceramic processing, you know that, for instance, inkjet molding or other technologies, extrusion-based technologies, often use some polymers as binders for ceramic processing. But in those cases, the content of organics is much lower. Here, you have at least a minimum 40 volume percent of a polymer that needs to be eliminated. And this requires, of course, a suitable thermal processing, which specifically means that you have to fire very, very slowly. And very slowly means that for a part this size, it takes 2 days, okay, from putting the part into the furnace and taking the part out. And you're going only to 600 degrees Celsius. And people have found that debinding comes better if you do it in inert atmosphere, because the decomposition is non-exothermic. In the decomposition of the organics is not exothermal in that case. If you burn out in oxygen, you have oxidative exothermal reactions that can lead to localized cracking. And then once you have your brown part, which is simply a non-sintered assembly of powders with the shape that you want, and typically these objects are very fragile, then you need to consolidate that. And you can do that by conventional sintering, and that can be fast. So you can see that you have a lot of issues with post-processing. You have issues with shaping in terms of how you spread the layer. So you need to have the correct technology for doing that. But certainly have a lot of post-processing issues. But of course, people that work in industry, they do their own calculations, and they know when it makes sense to use this approach for making parts that have the characteristics that you want and the cost that is acceptable. Before mentioning another couple of problems, let me just add that there are two more technologies that can be listed as VAT photopolymerization technologies that are not explained here. One is two-photon polymerization, and the other one is volumetric additive manufacturing. So there are some similarities, but between these two-photon polymerization, it's a technology that uses two different lasers. Where they meet, if the combination is right, you trigger localized polymerization. And this is a very nice technology because it can give you submicron features. So you can have a resolution of the order of 100 nanometers. But there are a lot of issues in terms of the size of the part that you can generate, typically a few hundred microns or few millimeters in size. And you have issues with the fact that for two-photon polymerization, you're basically generating your part, you're basically writing inside a volume of liquid. And if you do that in a slurry that is flowable, what happens is that the part will move while you are printing because you change the density of the part and you will not be able to have a precise shape. So for two-photon polymerization, the part needs to be attached to a substrate. You basically write inside the volume of the liquid, but starting from a substrate. And then if you have a ceramic material, then it becomes difficult to detach the part from the substrate for post-processing. So this technology has some advantages. I will show you some examples of that in my further lectures, but it has a lot of limitations. The other approach, that photopolymer volumetric additive manufacturing, has the advantage that it is not a layer-by-layer technology. It's much faster. Okay, it gives you very smooth surfaces. But in this case, it works very well with certain polymers. But for ceramic systems, you have the problem that the light has to go through not just the thickness of the layer, like in the case that the new layer that you are forming, like in the case of DLP or SLA, and the thickness of the layer is from 25 to 100 microns typically. But you have to go through millimeters of your feedstock. So the feedstock needs to be highly, highly transparent. And that's a challenge if you're using ceramic particles. So when we do it, we use colloidal particles or we use precursors. But volumetric additive manufacturing is an interesting technology with a lot of potential. In any case, coming back to VAT photopolymerization technologies, is some of the issues that you have when you are applying these technologies to ceramic-based feedstocks, especially if you're doing, let's say, conventional ceramics and you're using powder-based systems. You have problems with certain materials because of radiation scattering from the particles, so you do not have a good index matching between the ceramic particles and the photopolymer. Typically, the ceramic particles can have a refractive index much higher than that of the photopolymer. Or you have issues in terms of the fact that your particle absorbs. So for instance, silicon carbide, which is a very, very interesting and useful ceramic material for high-end applications, cannot be typically processed using this approach. Actually, now you can do it using some tricks, or either you use a high-intensity source, and I mean a polymeric DLP printer would have a light source that is maybe 5 microwatts per cubic, milliwatts per square centimeter. And for processing silicon carbide, you need to go 50, 60, 70 milliwatts per square centimeter. So you need expensive hardware. Or what people have done is to, since the problem is the absorbance, what they do is they oxidize the silicon carbide powder, and this creates a silica layer that does not absorb, has a low refractive index with respect to silicon carbide, and in this way you can consolidate the system. But then you have oxygen that you need to remove at very high temperature. The final issue that you have with this type of approach, but photopolymerization, so you have to disperse your ceramic particles into your liquid polymer. And people that make ceramics know that you can generate a lot of slurries quite efficiently, but typically they use water-based slurries. And there are a number of ways in which you can avoid agglomeration and precipitation of the powders. So you can stabilize ceramic powders quite effectively in water, chemically, or using stereological interactions between the particle. For non-aqueous systems, so if you have to disperse particles, ceramic particles in a polymer, the chemical ways of doing that efficiently are much more limited. So having a homogeneous slurry and stable slurry, because it takes, with conventional TLP, SLA, it takes hours to print a part. So you need to have a slurry that is stable for a long time. So this is certainly a problem for using these type of technologies with ceramics. But you can see here that people are actually able to use these technologies quite well. Here is different parts. They don't necessarily have any applications, the ones in the middle, but they show the capability of the technology. And these are parts made of lumina zirconia and calcium phosphate, which is a bioceramic. Another technology that has been used quite a lot for ceramic particles, for ceramic feedstocks, is binder jetting. Binder jetting has this specific working principle. You have a way of depositing your powder layer by layer. And after you deposit a layer of powder, you have a printing head that deposits a bonding agent. And the bonding agent binds selectively the powders that you have just deposited. And once you finish inscribing that layer, the part lowers, and then you coat again the part. You generate a new layer of fresh powder, and you repeat the process, giving a different shape. In this case, you can use inkjet printer heads, which have a resolution of a few hundred dpi, dots per inch. And so the quality of the surface can be quite good for the printing object. And what you are jetting is basically a polymeric binder, so diluted polymeric binder that can go through the small nozzles for your printer head. One issue that you have with this technology, this also would apply to selective laser melting and sintering, is that in order to generate your powder layer, you need what is called a flowable powder. And for instance, if you take a flour and you want to spread a layer of flour, which is simply very fine organic particles, you will see that it is difficult to achieve a thin, defectless layer of flour, because you have interaction between the particles, chemical interaction, secondary bonding between the particles, and this leads to the formation of a defected layer with cracks and inhomogeneities. And of course, if you do that with a ceramic powder, and I'm talking about fine particles because you know that if you need to sinter, you need high sinter activity.
And for ceramics, you use typically submicron particles for conventional processing. So if you use that type of powder, which is the one that you would normally use for making your ceramic part, then it is very, very difficult to obtain a defectless layer. So because those powders are non-flowable. In order to have flowable powders, there are ways of quantifying that and characterizing that. Basically, what you need to have is you need to have large particles, or at least something like 80% of your material needs to be constituted by large particles. And by large particles, I mean particles with a size of the order of 10, 20 microns and upwards. And this is great for flowing, but it is very, very bad for microstructure for ceramics, because then you have a green body that is constituted by large particles. And then after you eliminate the binder, these large particles are very, very difficult to sinter to full density, because simply you do not have the possibility to close the gaps between the particles after you remove the binder. So with binder jetting, it is impossible to obtain fully dense ceramic parts after printing. And bear in mind that I'm not talking about the porosity within the shape, the design porosity. I'm talking about the porosity within the solid. And typically, you want a fully solid part. The solid part needs to be fully dense because you need high strength for your part. There are only some applications where having residual porosity is suitable, and you can look forward to it. But from this point of view, the technology has two drawbacks. One is that the residual porosity for ceramics is of the order of 40 to 50 volume%, which is huge. And the second problem is that if you want to, you say that you would like to have a part that has not just the design porosity, but also residual porosity within the solid. But then typically you want to modify or you want to reach certain volumes of porosity that are suitable for specific applications. And there are not many ways of modifying the porosity in the solid that comes from the characteristics of that technology. Certainly, binder jetting has strong advantages because you can make a very large scale printing. I'll show, so you can see here, for instance, you can see the person there. So this is 4 meters by 2 meters type of bed, which is very, very good. And people use that for making, for instance, casting molds. Okay, you can use you can either use the liquid that you're jetting from the nozzle can either be this solvent-containing binder, or it can be just a solvent, and you can put binder particles together with the ceramic particles, and the solvent will locally dissolve the binder particles, joining the ceramic particles together. So you can see, for instance, that people have been using this technology for making some casting cores. I mentioned that you have residual porosity. One possibility is to fill the residual porosity using molten silicon, typically combined with pre-infiltration with a carbon source. And in this way, you can make siliconized silicon carbide, which is one of the good materials for a lot of high temperature applications. Or you can exploit the residual porosity within the solid. For instance, when you're making bioceramic parts, then having porosity within the solid helps with the connection with the tissues and vascularization and other transport of fluids within the solid. So for certain applications, binder jetting is good. Material jetting, inkjet printing. I was going to say that there are not many examples of this technology. Actually, there is an Israeli company that does that, and now there is also actually an Italian company that does this for ceramics. Here, the idea is simple. Instead of printing simply a binder, you're printing a binder containing slurry that contains also ceramic particles. So this certainly makes sense. It is a technology that on a 2D scale is used every day for decorating tiles, for instance, because you have jetting nanoparticles for generating colors, but you can do this in 3D. The problem is that conventional inkjet heads require nanoparticles, so you neither, otherwise they wouldn't flow through their nozzles. So you need either have develop your own feedstocks like this Israeli company, or like this Italian company has done. You need to redesign the jetting, the printing head and the nozzles through which you're jetting your ceramic particles. Otherwise, conventional approaches do not work. So these are some examples of what you can do, and you can see that in this case there are some limitations in terms of quality. But one of the advantages with this approach is that multi-component objects can be quite easily quite possible. I mean when I say multi-component, I mean multi-material, made of different materials, a single component made with different materials. The other technologies that I described, SLS, DLP, are not, SLA, sorry, DLP, are not that suitable for making multi-material components. We just acquired a 2-watt for DLP printer. Basically, what you do is that you have your sample is built on a support here, and you have 2 watts with 2 different materials, and the part built on one side, and then you clean, and then you build on the other side with a different material. You go back and forth with issues in terms of cleaning and lack of sharp interfaces and things like that. But with jetting, it's much easier to have simply feedstocks, different feedstocks, and generate different parts. It's easy to make graded structures, although you have some limitations in terms of aspect ratio. So powder bed fusion or powder bed sintering is a very good technology for polymers or for metals, because you can in situ melt or sinter particles, and in the end you can obtain a fully dense body. For polymers, this works rather well. For metals, you have issues in terms of the microstructure, but certainly you can get nice parts with it. So you can also use an electron beam for melting rather than a laser. So this technology, of course, is based on, again, depositing flowable powders. In this case, since you are in situ melting, and then you can reach full density, despite needing a flowable powder. For specifically ceramics, this technology which would be very nice because it would allow you to obtain a already sintered part after shaping. There are some difficulties because it is very difficult to obtain parts that do not contain significant amount of defects. These are old data. People are doing better things now. You can see some nice capabilities in terms of shaping, but if you then look at the microstructure, you can see that there are a lot of localized voids, and especially cracking. And this is due to the fact that you have very fast, very high temperatures, fast heating, and more importantly, fast localized cooling. And for ceramics, this leads to cracking because not all ceramics are very good in terms of thermal shock resistance. So I'm not familiar with any large-scale application of this technology for ceramics, while for the other technologies that I've described, there are a lot of examples. Directed energy deposition, this works well with metals. So you have a flux of powders through a nozzle, and then you use either a laser beam or an electron beam to locally melt, typically, or simply sinter, but typically melt your powders. And for metals, you can do that in the inner atmosphere in order to avoid oxidation. A variation of the powder approach is to use a wire. So you have a filament of your metal and you melt locally. So this is a very nice approach for metal particles. For ceramics, you still have the issue that you have very fast cooling, and that leads to cracking. And also for ceramic materials, you typically don't have a wire based on a ceramic material where you can do that. There are, and certainly there are also problems in controlling the microstructure. There are some examples rather successful of doing this using silica fibers or silica rods. And silica has a 0.5 10 to the minus 6 centigrade to the minus 1 coefficient of thermal expansion. So it's virtually, it's highly thermal shock resistant. So that's why you can locally melt. The melting temperature of silica is, well, the melting temperature is about 1700, but the glass transition temperature is about 1200 degrees. So you simply need to go to, let's say, 1400 degrees, and then you can have localized melting of your glass. And you do not have thermal shock because of the almost zero coefficient of thermal expansion. So you can see here some examples, successful examples for glass. People have tried this with ceramics, and you can see that, okay, they can succeed, but you can see what is the quality of the parts, and without just looking at the shape without even discussing what is the characteristics of the microstructure of the material. So another approach that is, of course, the first one that was developed for polymers. FDM actually is trademarked by, so filament deposition modeling. It was trademarked by Stratasys. A more appropriate way of calling it would be FFF, filament fused filament fabrication. In that case, you have, for a polymer, you have polymeric filament, and then you melt it through inside a nozzle, and then the nozzle deposits the material, and then the material cools down quickly. And this is very favorable because it means that the molten polymer can retain the shape that it was given by the nozzle. And you can use nozzles that go down to 200 microns in size, and this leads to very smooth surfaces. So this is, of course, again, a layer by layer process. You still have stair-stepping effects, but if the nozzle size is of the order 200 microns, the surface features are much less evident. So you can really get nicely looking parts for polymers. Before discussing another approach, which would be direct inviting, let me mention that you can do this with ceramics, but you have the problem that you need a ceramic filament or ceramic containing filament. And certainly you can say, well, people make polymeric filaments containing anything, so why not ceramics? Well, you can do that, but you cannot go above a certain volume of ceramics. Otherwise, the filament becomes too brittle and then you cannot, it breaks inside the printing head, and then it's a nightmare. So there are very few examples of people that are commercially available examples of people that are successfully making ceramic-based filaments. There's one company in France. I mean, you can find several ceramic filled filaments on the market, but most of them are not really optimized, or I wouldn't say trustworthy, but they're not optimized. There is one company in France that makes good filaments, but you need quite a lot of expertise in order to be able to print without having your filament break every 10 minutes. So this is an approach that has been more and more explored, despite being the first example, one of the first examples for additive manufacturing of materials. There is also another variation of this approach, which would that uses, instead of using a filament, so a nozzle, heated nozzle that melts the filament and generates a part, you have pellet extruder. So you're feeding to the nozzle where it gets melted, not a continuous filament, but pellets. And ceramic pellets are much easier to make than a ceramic filament, because for using FFF with a ceramic filament, the filament needs to be highly flexible, needs to be highly controlled in terms of the constancy of its own diameter and so forth. But if you simply feeding small pellets to the printer head, then it's much easier in terms of finding these and making these pellets. So you can make a bad filament, then you cut it into pellets, and then you have your feedstock, and you can put anything in it. One of the advantages of FFF is that it is material agnostic. What matters is the size of the powders for sintering, but you can put anything inside. So that's a great advantage. With pellets, they are easy to make. People that do injection molding, they use pellets. The problem with pellet printing is that it is difficult to have homogeneous flow inside the nozzle, because you have this assemblage of pellets that need to melt and create a continuous flow of molten material without voids. So the parts generated using a pellet approach typically have some internal defects, which is not desirable. Another advantage of these approaches, FFF or pellet extrusion, is that it is rather easy to make multi-material components. You simply need to have more than one filament or more than one extruder. So we have, for instance, a French printer that has 4 printer heads, where we can make components with 4 different ceramic materials. So this works quite well, with some advantages and disadvantages. Specifically for ceramic materials, people have developed what is called direct ink writing. So you basically write using an ink that is ceramic paste. And in this case, you do not need a lot of binder. You can have a lot of ceramic faces. Again, the material agnostic, you can use any type of ceramics. You don't have issues with scattering or absorbance of light and radiation and so forth. You typically would like to have this type of technology for generating parts that have complex shapes, or especially open parts containing open porosity. In this case, you need to control the rheology of the part quite accurately, but I'm not going to discuss that in this lecture, but in other lectures. So this is also used a lot for ceramic materials, direct inviting, because it has the advantage that you do not need to generate a filament. or pellets using this. So the optimization of the ink rheology means that you need a specific type of viscosity or rheological behavior. You need what is called a Herschel-Berkeley fluid, which is simply a pseudoplastic type of rheology behavior with yield stress. So, Newtonian flow, shear stress doesn't depend, has a linear dependence with the shear rate, dilatant. If you increase the shear rate, you increase the yield stress, and pseudoplastic is the opposite. So an example of a dilatant fluid is ketchup. So if you want to extract ketchup from your bottle, you should not shake it, because if you shake it, the viscosity increases and then it doesn't flow. So you need to be patient and apply and let it flow. For direct inviting, you need something like toothpaste. So if you have toothpaste, you open the tube and you do not want that to flow. You do not want to flow spontaneously. So the fluid has a yield stress. You need to apply a stress above a certain threshold. Then you apply the stress and the viscosity decreases, and then it starts flowing. But once the fluid comes out of the nozzle, then the viscosity increases because the stress is decreased. And therefore, if you have your bristles of your toothbrush, the toothpaste sits on top, doesn't flow a lot into your bristles. So for your ceramic feedstock, you need to engineer that type of properties or that type of rheology. You need to have a yield stress and you need to have a pseudoplastic behavior. And there are different ways in which you can do that. Of course, you need additives, and you can use fast evaporation of a solvent, but in this case, you might generate cracking. So you have to be careful. For FFF, let me just remind you, you do not have this issue. I mean, you still have the issue that you have a liquid layer that needs to be consolidated after being extruded. But in that case, you have the temperature that does it for you. Then as soon as the temperature cools down, is reduced, the viscosity of the polymer increases a lot. Here, you do not have, you have flow without temperature. So you need different ways of consolidating. And you can flocculate, coagulate the suspension. You can use reversible physical gels. For instance, if you add a little bit of colloidal silica, that generates a reversible gel. A high shear rate, you have an interconnected network. A low shear rate, you break down the network, and this is reversible. Or you can use thermoreversible gels. So you can see here, for instance, what it means not to be able to control properly the rheology. So this is a scaffold, a bioceramic scaffold. And this is the XY plane. So you're looking, so you're printing like this and you're looking in this direction. It looks very nice. But if you look in the cross section along the Z-axis, you can see that you have collapse of the struts or the filaments, because the recovery of the viscosity, the increase of the viscosity after releasing the stress was not fast enough. And if you optimize your rheology, then you're able to retain the structure that you want in your final part. So we're still talking about extrusion, either of a paste or of a filament, molten filament or molten pellets. And I mentioned that it's difficult to have to make these filaments, but this French company is able to make alumina. They make alumina zirconia, white and black. They make titania. They make low permittivity ceramics. They make silicon carbide, and they make ultra high temperature ceramic filaments. They just developed that. And we developed with them silicon nitride, but it's not commercially available yet. The filaments are kind of expensive, but I guess because it's, you know, they lead the market, so they can afford to do that. It's about 300 to 400 euros per half a kilo of filament. And so, yeah, but so it's not cheap. But they're able to make it, and certainly other companies will be able to make it in the future. One feature of this type of ceramic filaments is that they are engineered in a nice way, in the sense that, okay, you need flexibility. So you need to put in the specific type of polymers that allow you to do that. But it's a polymer-based system. And one polymer, which is a wax, can be solvent extracted. And right now, you have to use acetone, which is, from the industrial point of view, not the best. But I guess they are transitioning towards trying to use water-based, water-soluble polymers. But the main point is that you can, after you shape your ceramic material using this approach, you have about 30% organics, which is a lot in volume because, you know, zirconia is 5.5 grams per cubic centimeter, polymer is 1. Okay, so 30% organics means 50 volume percent organics. So you have a lot of organics that need to be decomposed. You cannot increase the amount of ceramic particles, otherwise the filament becomes too brittle and it simply cannot be printed. So you have this two polymer base binder. You chemically remove the one of the two components, and it's about, of the entire polymer, it's about 20%. And this creates some porosity, which is extremely useful because then the rest of the polymer is decomposed thermally. And you have a lot of gas that has to be released. And if there was no porosity inside the material, inside the solid part of the material, the part will break. So this is a very good way of being able to process components that typically maximum thickness is about 1 centimeter. If you go beyond that, then it becomes really, really, really difficult to obtain a crack-free part. So you simply need to live with that. And this will tie into my final discussion of this topic, why and where it makes sense to use additive manufacturing. So you cannot think of using additive manufacturing as a way of making all your components and everything you have been used to make so far, because there are limitations. So one disadvantage of this approach is that specifically for filaments, there are very, very few compositions commercially available. I wrote there borosilicate and zirconium silicate, because you can buy them, but they don't work. At least we haven't been able to make them work. So the last technology that I will mention, and then I will stop, is one of the first ones that was invented. So LOM, laminated object manufacturing. And this is not really a 3D approach, it's more a 2.5 approach, 2.5D approach. Basically, you have sheets of your material, and then you inscribe them, typically using a laser, and then you need to bind the layers together. And this can be done with sheets containing ceramic particles. It has been done with sheets containing particles, but this is not a technology that actually people use a lot for making 3D parts. And you have issues in terms of defects of the intersection between the different sheets. You can see here some examples that have been published. Peter Geyer worked on this, was the first one to work for ceramics. But basically, nobody, as far as I know, is using this industrially, and also there are not many laboratories devoting their time to this type of additive manufacturing technology, which is one of the 7 ones that have been identified by the ASTM ISO standard. So let me just finish here for this part of the lecture, and I'm open to receiving comments and questions.
So how can we improve the dispersion of particles?
So I'm an engineer, not a chemist. I think so there are people with a strong chemistry background who are looking at ways of coating the particles in a way that allow them to be dispersed, like you would do in a water-based slurry, but you need to use different chemicals, different mechanisms for stabilizing the particles. So there are a few papers in the literature that discuss that. Yeah, because the typical dispersants don't work well.
Then one of the slide you showed that the filament has more brittle. So if the filament is more brittle, then how can we fabricate, sir?
So, I mean, so the filament is brittle, but you can still use it. So one way is, for instance, to warm it up. If you keep it at 40 Celsius before you start using it, then for a while it is more flexible. This is something we do. The filaments that we buy specifically from one company, we've been quite successful in making parts, so they can work. But often you need to modify the printer, because for a filament printer, often the way the filament is fed into the nozzle doesn't work well with brittle filaments. So often you need to modify the way you are feeding the filament to avoid localized bending and other issues that would prevent you from printing.
Then in inkjet printing, sir, you talked about the rheology. So how do we control the rheology from our side? Is it possible to control the rheology from our side, or the material itself has inherently that particular property?
So for inkjet printing, so what the Israeli company does is to use bespoke, self-made, nanoparticle-based systems. And I mean, you certainly need the same type of rheological behavior. I don't think that they use this approach for making parts with suspended struts. So you're basically simply depositing on already existing material. And the company that has been developed in Italy, Northern Italy, it's a German company with a subsidiary in Northern Italy. They simply have developed a printer head with nozzles that can handle ceramic submicron particles, so 0.5 to 1 micron particles, and still obtain a good resolution in printing. And I'm not sure how they control the rheology, but you're right, that also needs to be controlled. Yeah.
Sir, what about the typical porosity level in these kind of additively manufactured ceramics as compared to metal additive manufacturing?
As compared to metal?
Yes.
Okay, so I'm not an expert in metal. I would say that the advantage of printing with ceramics is that my understanding is that the final microstructure after sintering is homogeneous in terms of the grain size, in terms of the grain shape, okay? While with metal additive manufacturing, you often have a lot of issues from that point of view. With certain technologies, so FDM, so all extrusion-based technologies, you can reach full density after sintering the ceramic part. So this doesn't mean that you have the same properties as you would for a part printed generated, same part generated conventionally, but you can reach full density. For SLA and DLP, you can still reach full density. It's a little bit more complicated because you have more organics to eliminate. And then you have, because of it's difficult to keep the particles suspended, and also it's a surface tension issue, you often have less particles at the interface between layers. So you have distinct layer features, and this leads to typically lower mechanical properties, but the part is fully dense.
But in the fully dense components, we have comparable properties with the conventionally fabricated ceramics, or?
So there are not a lot of papers that discuss that, because people simply want to show that with additive manufacturing, you can make shapes that are difficult to make with other technologies. So a direct comparison is not being made often. I think that people are becoming more better and better in obtaining high quality microstructures and parts, especially with DLP and SLA. So I guess you get, let's say, decent properties, good properties, maybe not exactly the same, because then apart from, it depends also on which property you're thinking of, because it's just the bending strength, or is it toughness? Okay, so we need to look at all the mechanical properties, and because of often more defects in these parts, you have a lower toughness with respect to conventional materials.
So one last question. So you were talking about different types of ceramics for this one. So most of the ceramics are generally allotropes, like it undergoes phase transformation at different temperatures.
Mm-hmm.
So will it cause any problem during the fabrication, since we are heating and cooling the material?
Well, that would apply to any ceramic material independently on the fabrication technology, because all ceramics are obtained typically by sintering, and you can have transit liquid phase sintering, or you can have a fully solid state sintering. So for certain ceramics, like silica-based ceramics, you have issues in terms of the transformation during cooling in that case, because you have the generation of phase with a larger volume that leads to cracking. But the problems are the same for...
But in case of conventional sintering, it will be like volumetric heating and cooling. So to some extent, we can able to have a control over the formation of cracks and so on. But here, generally in additive manufacturing, we'll have a gradient in terms of, we'll have thermal gradient. So different layers will undergo transformation at different situations. So,
well, no, because we are not applying heat after shaping a single layer. We apply heat to the entire body.
okay, so,
So
after that only we'll do sintering.
Yeah. So the apart from SLS, which is not used a lot for ceramics because of localized cracking, all the other technologies require taking the bulk part that you have shaped and sinter it, like any conventional sintering for ceramics. So from that point of view, that's not a problem. The problem is typically the fact that you have more organics that you need to burn out. So you have limitations in terms of thicknesses, you have much more extended processing times, and so forth.
Yes, thank you.